All right, it's a pleasure to be here celebrating 10 years at KIPAC, 7 for me. It's been a great 7 years. And I was asked to talk about big cosmological simulations. This is too loud for me. Can we turn it down? Sorry, I'm used to talking loud without a mic. Okay, so first I want to say what we mean by big in my context. There's multiple definitions of big in this case. One is the fact that the simulations that we're doing are quite often computationally expensive. They use a lot of memory, and they generate a lot of data. So that's one sense in which they're big. They are also big in the sense that we are trying to simulate essentially the entire universe, and we need to simulate that entire universe, including a lot of detailed physics. So we have a very broad range of scales that we're interested in. And it's also big in terms of the complexity of the models or the predictions. And I'll be talking about various flavors of these models here. So first, I just wanted to start by talking about what are the kinds of problems that we are trying to solve where simulations might be useful, right? One is basically to learn how some sort of physical process occurs. And in many cases, you would like to ideally write down how that physical process works on pen and paper. But essentially, the complexity of many problems, the fact that they are very nonlinear, or the fact that they are very multi-scale, means that we're driven to use simulations instead of analytic models. The second thing we might want to do is infer the parameters of some model or distinguish between different models using some data. And in order to do that, we need to, first of all, really be sure what are the predictions of that model in the observable space. Okay, and that quite often requires simulations. A third kind of thing we might want to do is actually, we've got a particular object in the universe, and there's some things we can measure about that particular object, but we'd like to infer some things that we can't directly measure, its physical properties, or, for example, its history. And then the fourth thing, sort of related to the third, is we'd like to connect populations in the universe across time. We heard about this yesterday from Peter, Mariska, and Dan. This is certainly one of the goals in cosmology and galaxy formation, is to be able to do this. And all of these things, I think, really require or are strongly improved by using simulations. So in cosmology, we're now at the stage where we're trying to get to sort of better than % level accuracy. And so we really require very precise predictions. In galaxy formation, as we heard from Elliot yesterday, we have to actually be able to resolve GMCs, very small, and we want to be able to do that at least over tens of megaparsecs, and if you want the full galaxy population, actually probably hundreds of megaparsecs. And so we need simulations to do both of these things, and the simulations that we really would like to have are well beyond our current capabilities. I think for both of these problems. And so we need to basically figure out smarter ways to do things. Some of those things I have ideas about, and many of them I have no ideas about. And so I hope that you all will have some. So I'm going to talk about 3 example science questions, and obviously in 20 minutes I'll only have time to touch on a few aspects of these 3 science questions because they're all very rich. So one that many people are interested in is, what are the cosmological parameters of the universe, including what is the nature of dark matter and dark energy and inflation, inferred from a survey of galaxies, like the LSST, or more near term, the Dark Energy Survey, which started this week, many other surveys. So we need to do simulations in order to do this. Those simulations are expensive, and what is the best way to sort of explore that parameter space effectively and make use of the limited runs that we can do, and how do we most effectively compare the models to data? A second question is, how do galaxies form? We heard yesterday this discussion about what are we taking as assumed? What is the point that we're starting from? And I think here we're also in a situation where we want to really explore model parameter space, but it's very computationally challenging to do so in a variety of models. A third kind of science question is, what are the physical properties of some object? And I'll talk about the specific case about inferring the physical properties and formation history of our own galaxy using simulations as an informative prior. Okay, so in a survey like LSST, you're going to map out the galaxy distribution and how it evolves over time. And what you'd like to do is use that to infer in gory detail what are the cosmological parameters. But in order to do that, you need to first understand how these cosmological parameters are related to your observables. And so you need to understand how to go from those cosmological parameters to detailed predictions for the formation of structure and its relationship to the observations of galaxies. And so just want to go through some details in this step. Okay, so the first step is to get from the cosmological parameters just to the evolution of structure as mapped by the dark matter distribution. This one is sort of under control in principle, and by that I mean we understand what physics is relevant on the relevant scales if we're talking mostly about large scales, and we know how to calculate that, but it's very, very expensive. So this is just a series of simulations which span a range of scales from less than a megaparsec, sort of the size of a galaxy, simulated here with very high resolution, out to a few gigaparsecs, which is still actually smaller than the sizes that will be probed by the next generations of surveys. And so Lambda CDM makes very robust and testable predictions for these, and that is really the basis of what we're using to probe dark energy, dark matter, and galaxy formation. But it's quite computationally expensive to do so. So in this context, right, this is just a movie of the evolution of the matter distribution in a small box. What people generally do is take this very complex picture and simplify it to some summary statistics. So some examples are the halo mass function, the halo correlation function. What you're watching here, I'll show this one more time. What you're watching here, the gray is just the dark matter distribution. The colored points here are halos of specific masses, and those halo mass ranges are color-coded on the mass function. Right, so this is one of the most informative statistics here, but there obviously is a lot more information in this cosmological box, and I think we still haven't yet really figured out what is the optimal way to actually get all of that information out that we actually are measuring with surveys and test it with these models. So here are just a few of the challenges that I think are important. So the first is that we need these predictions to be very, very accurate, and we are measuring these things with sort of better than percent level over a very wide range of scales, and so we would like to be able to make predictions at that level. So simulating this full dynamic range of interest over the full range of computation of cosmological parameters of interest is sort of well beyond our current capabilities if we just brute force it. And that's true even if you're just worrying about the dark matter. It's true probably by a few orders of magnitude more if you really want to understand the baryonic physics and its impact. And that probably is not essential on large scales, but there's significantly more information as we go to smaller scales, which we can make use of if we're actually able to make accurate predictions of the distribution of baryons. So I think there are big outstanding questions in sort of what are the best ways to explore parameter space and what are the best ways to compare models to data. And then one other technical note is that for many problems, we are now in the stage where we're becoming more and more data limited. So, and by data, I mean both disk and memory and network rather than CPU. And it's a relatively new situation in this. It's not true for all problems, but it's true for many of these problems. So just on the dark matter side, here are some strategies that may help us with this computationally challenging problem. One is to do things in a multi-scale way. Don't simulate everything, don't simulate the entire universe at high resolution, but pick specific regions of interest where you care about this. We are going to have an unconference session today, which is called ICing in the cloud. So IC stands for initial conditions. So the idea of this unconference is to develop a way so that people can sort of register their initial conditions for their simulation in a way that makes them actually usable to other groups and their own future studies. And I think many of us are quite excited about this. So any simulators who are interested, any observers or statisticians who want to contribute, all of those things would be welcome. Because I think one of the things that we really need to do moving forward is be able to do this in a more modular way and to be able to compare different codes more effectively. So one of the ways to, so far the way people do this generally, in the crude way, is they do a simulation for some cosmological model and they look at some of these statistics and then they, make some fitting function or sometimes an analytic model which is a function of cosmological parameters. And I think there's a lot of room for improvement here. So there's some work being done on emulators. So these are just two examples of where what you do is you try to sample the parameter space of interest with a limited number of points and then just do the simulation for those limited number of points. And then it's essentially a fancy interpolation scheme, okay, between those. And so far people have really just done this for really some of these simple statistics like the power spectrum. So there's a lot more to do here, either in doing this for other statistics or in figuring out better ways to think about this problem. An alternative to this emulation thing is the idea of rescaling. We actually do have some understanding of what's happening as you change cosmological parameters analytically, and so there are ways to basically do a very expensive cosmological simulation, rescale it to another cosmology. And I think this is a very promising idea. I don't think it's yet clear what accuracy is possible or what scales are viable to do with this kind of technique. So lots of interesting things to think about there. Okay, so I've just talked about getting to the dark matter distribution. Now we'd like to get from the dark matter distribution to predictions of galaxy properties. We heard yesterday about the challenges in doing this from an ab initio point of view. We certainly do not currently understand galaxy formation with the accuracy that we can measure it. But there's a lot of success with various empirical models. This is just one example of work from my group, led by Rachel Reddick, who's here. In this set of plots, don't worry about the details, but the black lines are data, and the blue lines are a model. And this is a very simple model. This is a model that basically had two parameters. And we're able to match these detailed statistics. Okay. And this was done basically by assuming that you have one galaxy in every dark matter halo and that there's some relationship between those things. In this case, we're just predicting one galaxy property, stellar mass. So if you want to predict more galaxy properties, you probably need to do something a little bit more complicated. The other thing is this required very high resolution simulations. We went one step further. You heard about this a little bit from Peter Baruzzi, and Mariska talked about this yesterday. Combining these techniques of statistically connecting galaxies and halos at one epoch with our understanding of how dark matter halos grow over time. Okay? So this is still really an empirical model, but it's now an empirical model which actually reproduces galaxy stellar mass functions and star formation histories. And I think there's a lot of basic understanding about galaxy formation that you can get from these kind of empirical models. You saw the plot that Mariska showed yesterday that we inferred on the constancy of the galaxy formation efficiency over the last 10 billion years that came out of this kind of work. So again, lots of progress, but in these empirical models, but they only go as far as they do. They're not really explaining the galaxy properties. And these simple empirical models require very high resolution simulations. If you have lower resolution simulations, I think the models are still much more complex. And so in order to do this, we need either very expensive simulations or better predictors. I also think there are significant challenges in actually using all of the data that we have, in particular in combining diverse data sets with different levels of uncertainty to constrain the models. So if we want to go one step further and actually understand something about the galaxy formation physics, I think it's even a step harder. So, in cosmology, it's at least relatively simple conceptually. We have a model that we're trying to test. That model has some parameters. And we do actually know how to make predictions for that set of parameters. And I don't really feel like we're at that stage in galaxy formation. Essentially, all galaxy formation models have parameters. That's true even of hydro simulations, where there are a bunch of empirical recipes that are put in. It's certainly true of semi-analytic models, which are sort of the most physical models that one can really rapidly explore. But this is a challenging thing because we don't really have a working model that matches the data. So it's not like you really are properly exploring parameter space. I think this is a big challenge. But I think with a limited set of observables, we're starting to ask these questions in sensible ways. And you heard a little bit about this from Yulu yesterday. So I just flash this plot up as an example from his model. This is showing his, I think, 12-dimensional parameter space where these parameters specify sort of parametrized versions of galaxy formation physics, like how the supernova feedback scales with halo circular velocity, this kind of thing. So I think this is absolutely a huge step in the right direction, but there are still a whole bunch of challenges, and this is just my opinionated view of some of these challenges. Most papers in the literature still sort of fix some parameters and constrain a few just by kind of looking to see whether the plot fits. I mean, there's still a lot of papers in this game that are published in this way. And there's now sort of a handful of papers which really have some well-defined parameter space that they're exploring, and then they consider the posterior for some other observables. But this parameter space is complex and correlated, and it's expensive to investigate it. And most models are not really yet accurate enough to match many basic statistics at the level they can be measured, and you talked about that yesterday. And so there's lots of room for progress here, and I think this is a place where better statistics, better computation, and a better understanding of really how to deal with diverse data sets can really help us. Okay, so now I want to get back to this problem of how to infer the cosmological model from observations of galaxies. Many people who are working on dark energy problems aren't really interested in the details of galaxy formation, and so that comes under the label of astrophysical systematics. And so in this case, you might not care what supernova feedback looks like. You just care about how the galaxies and halos are related. But you still have a lot of challenges. You need really realistic full simulations to understand your systematic errors, but each realization is expensive. And so we need to not just go from the matter distribution to the galaxy distribution, but also to what you would actually see from that galaxy distribution after it gets out of the telescope. And there have been a lot of effort on this last piece, in particular by the LSST team, which is now simulating the impact of the telescope and the atmosphere, sort of photon by photon. So an example of this being expensive for the DES survey, we've been simulating, so about double the DES survey, so more than 1 billion galaxies over a quarter of the sky. Doing that takes, from the initial conditions to the galaxy catalog, takes about 750,000 CPU hours. Whoops. And so that includes the dark matter, the galaxies, actually measuring the shear, putting in photometric errors, predicting the distribution of galaxies, including the lensing. And what we're embarking on now with the collaboration is really trying to engage all of the science working groups in doing their science on these simulations before they have the full data set. So to actually take these fake galaxies and infer cosmological parameters and see whether they got it right, I think this is actually an essential exercise. I really don't think, personally, that we should be able to publish cosmological parameters on the data if we can't get it right in this more simplified version. And this is still early games in this for astronomical surveys. It's similar to things that have been done in particle physics. But there's still a lot of challenges. I mean, to really convince yourself you've done this right, you know, you'd like to be able to properly evaluate the posterior of all of the uncertain systematics and the physical parameters given your data. And we're not really there yet. Okay, I'm almost out of time, so I'm going to just take 2 more minutes. So I had a conversation with Sam Skillman yesterday at the dinner about why are people still showing this image so much. This image is about as old as KIPAC. So this is almost a 10-year-old image. So it's interesting. So this simulation is no longer state of the art. We could, you know, I mean, it was heroic at the time for sure, but people have done many other such simulations. But I think the main reason is that access and usability and pretty pictures matter. So I think that's a really important lesson for us and is something that will really, hopefully if we really think hard about these issues, will allow us to make more progress. So unfortunately, I'm going to have to skip my 3rd example, and I will just, sorry about that, and I will just end here and say, you know, the things that I really think we can make progress on in the next 10 years, creating better tools, figuring out ways to make the data more accessible, really figuring out what are the optimal ways to approximate these computationally expensive problems, understanding the parameter space in which we should be comparing models to data, and you know, what is the optimal combination of the kinds of learning and inference techniques that we'll hear about in the next 2 talks, and potentially the crowdsourcing that we heard about in the last talk. Thanks.
You said that you start to be limited by network and storage. Can you give numbers? Do you have an idea of what's the size of the problem?
Yeah. I mean, you know, the kinds of simulations that we are doing end up taking about 5 terabytes per run. And that's what we're doing currently for DES. And, you know, so then a lot of that we want to serve to the entire collaboration. We want to be able to do that many, many times in order to explore parameter space. So that's sort of order of magnitude, but I'd be happy to talk about the details.